Okay, hi everyone. Welcome to the 7th Cosmic Conversations talk of the year, and it's also going to be moving towards an end soon. And today we have Busisiwe doing a talk on her master's work. Now, she studied at the University of Venda for her BSc and her honors degrees, and now she's doing laser physics under the supervision of, I think, Professor C and Dr. Steenkamp. So, thank you, Lucy. Yeah.
Thank you, Gerald. Hi, everyone. Okay, so for my presentation, I will be talking about the application of X-ray-based system being used as non-destructive testing method on additively manufactured samples. My study is motivated by the fact that additive manufacturing has a very important role when it comes to various industries such as the aerospace industry, from building complex geometries into joining different parts into one functional part, to medical field where medical implants are printed with additive manufacturing method. That is why the quality control and the non-destructive test method are very important when it comes to its adoption and the ensuring structural integrity of the additively manufactured parts. And therefore, the application of X-ray phase contrast and dark field 2D imaging can provide additional benefit through and improve contrast and easier identification of defects in additively manufactured parts. The main aim of my study is to use the application of phase contrast and dark field 2D imaging on aluminum alloy additively manufactured samples. The purpose in this is to try and see whether I'll be able to detect intentionally created porosity with various distribution, like pores with open and pores with some trapped powder in it. And then from there, I'll be able to tell whether this imaging method is suitable to be used for non-destructive testing. So as I start, I'll be starting with basically giving a brief view of what additive manufacturing is and focusing it on laser powder bed fusion, and later moving on to the non-destructive testing method that is mostly used in industries, which is computer tomography, and then speak about the phase contrast and dark field imaging, which is based on the Talbot-Low interferometer. And then from there, I'll just give a brief review of the results from a paper where they are demonstrating how they used the system that they're going to use, and close off with some present and future work. So basically, when you talk about the laser powder bed fusion, additive manufacturing, we are talking about the production of materials through addition of materials, the build materials in layer by layer mode. And then from an ASTM standard 52900 of 2015, there are about 7 process categories, in which 5 of them have a very huge difference among its properties, and therefore declared to be having lower readiness level, and they are not mostly applied, unlike the first 2 methods. The first 2 method, which is direct energy deposition and the powder bed fusion. The directed energy deposition is energy to fuse the material as it is being deposited through melting it. The deposited material can either be powder or a wire in this case, while the thermal energy source can either be a high energy electron beam or a laser. And then the one that we'll be focusing on is in powder bed fusion. In powder bed fusion, they use a thermal energy source to fuse the powder in selective region when printing the material. And then in this case, the material that is being deposited as compared to direct energy deposition is just only powder. But the thermal energy source that is being used here can either be an electron beam or the laser. The one that uses electron beam is called electron beam powder bed fusion, while the one that uses laser is laser powder bed fusion. So in my research, I'm focusing on laser powder bed fusion. So what happens in laser powder bed fusion is that in the build platform, we have a base plate where the deposition, the material is being deposited. And then as it is being deposited, we'll be having a laser scanning system that moves in the direction of the 3D design. And as the laser moves, it melts the powder, but then as it moves away, the powder tends to be solid. This forms what we call track. And then from the number of tracks, we can be having layers and eventually having the full 3D parts that we are looking into or working into printing. And then the disadvantage with this method is that during the printing, there can be several things occurring. One of them is that as the laser is forming the layers, there may be weak bonds formed within or between the layers, and that is what we call, that's a defect which we call a lack of fusion porosity. And another one can be that a depression well filled with vapor may collapse and form some holes with a keyhole shape. That is what we called a keyhole porosity. And the worst of them can either be a gas trapped in the melted pool or some powder being trapped in the cavities, and we call that one the spherical porosity. But then it is not so ideal to physically cut through your object after you've printed it. That is why we have what we call non-destructive testing, which enables us to see through the object without having to cut it physically. So the most used non-destructive testing method is what we call computed tomography. Computed tomography has two systems, which is the first one is the nanotomic computed tomography, which is a high resolution scanning system that is designed for samples with radius less than 10 millimeter. And it has a maximum voltage that is restricted to 180 kilovolts. And because low energy X-rays can be stable over a long period of time, then the scanning period for this type of method normally lasts between 1 hour and 4 hours, depending on the image quality and the type of resolution that we'll be looking at. And then the next one and the mostly used one is the microcomputed tomography. It is basically a walk-in cabinet that is designed to be used on large samples with diameter between 10 millimeter and 300 millimeter. It has a transmission tube and a reflection tube. And the scanning process duration for this one normally lasts between 30 minutes and 1 hour and 30 minutes. So how this process takes place is that we'll be having a sample put in a rotation stage between fixed X-ray source and the detector. And then the sample will be put in such a way that it is perpendicular to the X-ray beam emitted from the X-ray source. And then as the sample rotates through 360 degrees, the X-ray photons will be passing through and around the object, forming shadow images of the samples that is being scanned on the detector. And then from there, the 2D obtained images can then be constructed into a 3D data set and an image analysis software, and in this case we are using Dragonfly software, is used to analyze segments and visualize the data into what we are basically looking for. So now we'll be talking about the phase contrast and the dark field imaging. It's a type of imaging that is based on the principle of Talbot-Lowe interferometer, which basically uses 3 types of gratings during its whole imaging process. What we have is the absorption grating, which is put just directly behind the X-ray source. What the absorption grating do is it produces transverse and coherent beam, which is then passed through to the G1 grating, which is called phase grating. The coherent beam that is passed through into this type of grating can be observed at the Talbot distance given here, whereby P is the period and lambda is the wavelength of the beam. And then what is special about this type of grating is that it produces or it imposes what we call phase modulation, and phase modulation will then create intensity modulation. The intensity modulation can be analyzed at this grating, the G2 grating, which is called the absorber grating. So after the setting has been done and the distance between the gratings are kept at minimum, what we will see on the detector over here is what we call more fringe. More fringe visibility is actually the intensity modulation of the fringe, and it is measured by taking the ratio of the distance between the maximum intensity and the minimum intensity. And then once you have this more fringe, you can work with the pattern by fine-tuning it into you can work with this more fringe by fine-tuning it by using a micrometer screw on the last 2 gratings and getting image reference for the 3 modalities, which is the absorption contrast, the phase contrast, and the dark field imaging contrast. The fine tuning is done in such a way that there will be around the optical axis, there will be, I forgot the term, but it's a rotation up around the optical axis, but hopefully I'll remember it. And then from there, we can be having what we call contrast signal, which are in 3 forms. One of it is the attenuation, which is basically the reduction of the amplitude that is resulted from the absorption. The second of it is the differential phase contrast, which is differential phase contrast signal, which is obtained when there's a change in refractive index, hence causing a phase shift. And then the last of it is when there is multiple scattering, then the interference pattern tends to be reduced, and this produces what we call the dark field signal. The system that we are using to scan, or the system that we are using, the one I keep on referring to as the X-ray, phase contrast, and dark field imaging, is a talent version type of a system. It basically uses the phenomenon I've just explained with the 3 gratings. It actually offers a systematic and simple way to explore the potential of phase contrast and dark field imaging. Because I have not yet scanned my sample with the phase contrast system, what I've done is I've just taken out some images that give a brief demonstration of how will my results be after I've scanned the samples. So looking at this sample is a tensile sample that was also used in the paper as a test sample to demonstrate how the system works. So basically, when we look on the first image, on the absorption contrast image, by the notch of the sample, there is low absorption, which is caused by a reduction of the cross section. However, what they then did is they broke and pulled out the fibers in the samples, and then because phase contrast enables the enhancements of edge detection, they could then be able to see the parts where the fibers were pulled. And then because this tensile sample is a carbon fiber tensile sample, and with carbon fibers, what you know is that it increases the X-ray scattering. So that was seen on the dark field imaging, whereby where there are no dark field, where we are not seeing the scattering is the parts where the fibers were pulled out. And then what I have done so far with my other team is we looked at the measurement of porosity with different methods. It was an aluminum sample, 6061 type of an alloy sample, which we used to measure those porosity through Archimedes, the gas pygnometer, and a computed tomography method. This type of measurement was motivated by the fact that even though we know that computed tomography is a very good non-destructive testing method, but then it takes long and it is quite expensive. So we know, on the other hand, that the Archimedes method is quite affordable and easy to use. So what we did is we took a number of measurements. We did number of measurement in 3 different days, and in those 3 different days we got different measurement. And in Archimedes we could both in Archimedes and the gas pygnometer, we were taking precautions the more we went that side through, instead of handling the samples with hand, because there could be some oil transformed from your hands to the samples. We were then using optical tweezers to handle the samples, and there are more precautions that we took. And then with Archimedes, what we obtained is that a number of samples were having higher density values, with 42% of them having density values above the theoretical density from the literature. So as we went there, we still got different results. So what we did is we took the lowest porous sample and used it as the reference density. And from the results we got there, we compared the results we obtained from the computed tomography and the Archimedes, and we could see that both the Archimedes and the CT had porosity that is less than 0.5%. However, the correlation is very poor between these two methods, and this could be due to the fact that even though the Archimedes can miss porosities that are especially filled with powder, the computed tomography can also be having other issues like lack of resolution, and also missing and I mean errors in the segmentation, such as missing those very small porosities, and hence the lowest porosity values when compared to Archimedes. With gas pygnometer, the reason we did not compare it with the two methods, it was because it gave us very erroneous values with porosity greater than 8%. That was the minimum porosity values we've got. So from these results that we have obtained, we then concluded that with X-ray computed tomography, the results are pretty much reliable, and it is giving us visual information. And so for the range of the porosity that we had, that is less than 0.5%, we basically concluded that for future studies that will also be looking at these methods can consider looking at wider range of porosity greater than 0.5%. But then in this case, looking at a range of porosity acceptable or that makes sense for each method and possible limits in each method. And then for my individual research, what I did is, because I'm looking at creating porosity intentionally so I can be able to use the different X-ray based system for non-destructive testing, is I printed a 3-batch of samples of aluminum samples that has some silicon and magnesium element. These 3-batch, the difference between them is the base plate temperature. The base plate temperature was one of it was preheated at 100 degrees Celsius, the other one at 200 degrees, and the last one at 300 degrees Celsius. The parameters, the printing parameters were all the same. The difference was only just that of the base plate temperature. So even though with most of the studies, when they've preheated their base plate temperature, they tend to get lowest porous samples as you increase the temperature. With me, I've got the opposite of it. The porosity levels increases as you move from the lowest preheated base plates to the highest preheated base plates. And this is mainly caused by the fact that the laser powder bed fusion is nonlinear. A change in a single parameter can change various parameters. And also it does not only depend on the base plate temperature. There are other parameters that, like the laser scanning power, the scanning speed, and various other parameters. So I'm still looking into what exactly did cause the change in this porosity. However, what you're seeing here is just the first image printed at the preheated base plate temperature of 100 degrees. And this one is the very last sample number 26 of which was printed at a preheated base plate temperature at 300 degrees. And from what I've got here, I've concluded that for now, since my most porous samples are the ones that were printed at 300 degrees Celsius preheated base plate temperature. So I'm currently doing a full CT scan on those samples printed at this base plate temperature. And then from there, I'll be moving to do the phase contrast and dark field imaging at VETS, and then compare the results and conclude in terms of whether I can use the system as a non-destructive testing method. Sorry.
What facilities do you use to print that?
Okay, so this sample, the aluminum sample were printed at a company in Poland, and then the scanning of computed tomography is done at the Department of Forestry, just after you close up by academia student accommodation. And then for the phase contrast and dark field imaging, we don't have such systems here. We'll be printing the samples we'll be imaging the samples at VETS. So in closing, I'll be liking to thank my both my co-supervisor and my main supervisor for granting me such an opportunity to work under their supervision, their continuous guidance, supports, and daily valuable inputs. I'm also grateful to this institution for granting me the opportunity to further my studies. Mr. Governor by the engineering building, who was very patient with us since we had to come for several days and taking longer hours in doing the measurement. Miss Colleen at the central analytical facility for always working us through the journey of understanding how CT works, the collaborators who were very helpful in printing the samples, the Rabdasa team who worked along with me in doing the different measurement of density, the financial support from NRL, and lastly, I'm grateful to the organizer and everyone who took their time and come and join us in this conversation. Thank you.
If anyone has any questions? Okay, great.
The previous alloy example that you mentioned, did you say that you use all
Sorry?
for the previous example, the alloy samples that you used, did you say, and I misheard, did you say you use optical tweezers to manipulate them before you image them?
No, I used the tweezers when we're doing the Archimedes and the gas pygnometer density measurement.
Did you move the sample? Is the sample in some kind of medium?
No, it's just for the density measurement, it was a cube sample of 10 by 10 by 10 millimeter. It's an aluminum sample, so it's not liquid. It's a metal aluminum sample. It's just that for the density measurement, we use 6061 type of an aluminum sample, and for my research, I'm using the one of aluminum, silicon, and magnesium.
So you said that there's these two methods, and like each of them has strengths. Like this one is good at big pores, or this one is bad if it's gas filled. How do you know which one is not correct, but how do you benchmark whether your results are good or not? Like, what is the absolute test of it? How do you know which one you can trust?
By doing several measurements, okay, for gas pygnometer and the Archimedes, we had to do several measurements and compare the results if the difference between the results was very huge or very low. And then for CT, we only did one scan, making sure that the scan is of a quality scan with less artifacts. And then from there, to ensure that you have the correct results, you can use different software analysis. And then if those two software or more than one software give you the same results, it shows that the method is accurate.
Okay, great. Thanks, Lucy.